Assalamu alaikum everyone and welcome to this video. So what we'll be discussing now is the chapter of lenses, and it's linked very closely to the ideas that we did in light, but a lot of people, even though they have good grip on the unit on light, they often do struggle with lenses. So this is a video that is aimed at basically going through it all again, all that the chapter requires and how the questions are asked. So first of all, if we just talk about the idea of lenses and what they are, so they're just devices made of plastic or glass that use refraction of light, something you would have done if you have covered light before, to form images. Now there are basically two categorizations of lenses. The one on the left is called convex or converging. Both of these are names used to describe a lens that looks like this here. And both of these names come from different ideas. The name convex comes from the shape of the lens. So as you can see, this is thin around the edges, but it's thicker through the center. And why it's called converging is because the light rays, after passing through the lens, come together, right? So they converge. So they meet at a point. If I were to just show you this regarding this idea regarding this diagram, how you can see it is using the bending of light. So first of all, if we just talk about this ray, which goes through the center of the lens, this is called the optical center O, as we'll also define. It does not bend. And the idea is really very simple. It's not even something you have to learn by heart. You know that at this point, if I were to draw a tangent, and I would need to draw a tangent to draw the normal, because this is a curved surface. So the normal would look like this. So the angle of incidence is 0 and the angle of refraction is also 0. So this light ray, it just goes straight through here. The other places there is going to be some bending of light, for example like this, and then it's going to bend further. Again, why does light bend like this is because, again, if I were to first make the tangent, then the normal at the surface, so in going from less dense to more dense, so this is how the normal looks like. So in going from less dense to more dense, light bends towards the normal. That's what we can also see here. This light would have gone like this, but it's bended slightly like this. Again, my construction of the normal is not 100% accurate. And similarly, the normal in this case, after drawing the tangent, it would be like this. So light should have gone like this, but it bends away from the normal in this direction shown. So this is the behavior that we see with these light rays. So the light rays, they meet, they converge at this point. We'll also be officially defining this point in a while. So this is how the rays go. So let's just mark these to show the action of this converging lens on this parallel beam of light, because all the light rays previously are parallel and then they are brought together by the action of the converging lens. Similarly, the other shape is called concave, and the name, it's very easy to see because this lens is caved in from both sides. Again, if I were to just talk about the shape, so this is thin through the center, but it's thicker around the edges. And why is it called a diverging lens is because the light rays diverge and they basically spread out after passing through this lens. So again, pretty much the same idea as with the converging lens. This one is not deviated because of the same reasons. This one bends out at each boundary. This one also bends out like this. Similarly here, and like this. So that's how we can show the bending of light in this case. All right, so this basically shows the action of the diverging lens. As you can see, the light rays are spreading out. So that's how both of these lenses work. And in our syllabus, we'll basically be restricting ourselves to just converging, or what are also known as convex lens. Now, to further talk about lens, we must define some basic terms. These terms are these. So first of all, the optical center is defined as the geometric center of the lens. So what basically just looks like the center, that's called the geometric center. You must have also heard this term back when you were doing moments, when you say that for a regular object, the center of gravity, the center of mass is the geometric center. So what just looks like the center at site. B, the focal point. So the focal point is the point where rays converge after passing through the lens. So again, this is in the context of the converging lens. That's when we see the rays to converge. The principal axis. So this is a imaginary line through O, the optical center, and perpendicular to the axis of the lens. The focal length is the distance between the optical center O and F. Now we'll also be seeing all of these on the diagram. The focal point, let me just go up and label this here. This point where all of the rays were converging here, this is the focal point. And it's really, really important as far as drawing the lens ray diagrams are concerned. All right, so let's say this is our lens. If we have to mark all of these terms that we defined onto this lens, so this is going to be the optical center, right? So by sight, halfway along this length, halfway along this length, that's the optical center. Next, I'm going to label the principal axis. Again, so it's the imaginary line through O, but perpendicular to the axis of the lens. So if I just look at the lens right now, it's standing about this line. So that's the axis. So the principal axis is a line that's perpendicular to this axis. So it's going to be like this. So that it's perpendicular to this axis. All right. Apart from this, the focal point, which is also known as the principal focus in some older texts. For example, if a ray comes in like this, parallel to the principal axis, the point which it passes through on the principal axis, that's F. And the focal length is this distance between O and F. So this is the focal length. You also see a star here because that's going to talk about something related to the focal length. So the idea is this, that the focal length is basically an indicator of the power of the lens. Some of you may have glasses and you may have heard the term the power of the lenses or the power of the glasses. That's basically referring to the focal length. Now think about this example for a second. Let's say that if I have a more powerful lens, it would bend the light ray more. So instead of passing through here, it would maybe pass through here. And then it would intersect the principal axis first. So this length would be shorter. So that's an indicator of the power of the lens. So the idea is this: the smaller or the shorter the focal length, the more powerful the lens. All right. Now let's go on to the rules for drawing the ray diagrams. So rule number 1 says this, and again these are just rules that you need to learn how to use in order to complete the ray diagrams. So a ray which passes through O remains undeviated, so it does not bend. If I were to just show you this rule in action. So it means that if you have a ray which goes through O, it's totally undeviated. In reality, we know that it would be bending slightly between these two boundaries, between here and here, but again, it just all evens out at the end of the day. Similarly, a ray like this, it also remains totally undeviated. This is the easiest rule, and this is something you should draw first whenever you have to make a ray diagram. The second rule, a ray parallel to the principal axis gets refracted through the focal point. So in the previous cases, we were drawing the bending of the ray here and here, but just to simplify this, we'll now always be talking about it in this way, that if this is the axis of the lens, it just gets refracted at the center. It's not true, but it's a simplification. It makes the drawing more convenient. So when this gets refracted, it's going to bend like this. This point that it passes through, this point is the focal point. All right. The third rule is this, that a ray which passes through F gets refracted such that it becomes parallel to the principal axis. So a ray like this, if it's already passing through F here, it gets refracted in such a way that it becomes parallel to the principal axis like this. All right, so these are the three rules. Now, to complete a ray diagram, you just need to use any two of these rules. You should always be using this. My personal preference is 1 and 2. You could also do 1 and 3. 2 and 3 would also work, but it's not recommended. 1 is the easiest rule to use. So you use any two out of the 3 to complete the ray diagram. Now, what are the steps? So using the focal length given, and this is what most of the questions in paper 2 would be like. Whenever you are given a graph paper and you have to make the entire ray diagram drawing, this is the steps you would follow 90% of the time. Using the focal length given, this will be given in the question, you will mark F and 2F points on either side of the lens. There's also a star here because sometimes the examiner will give you a scale, so you have to take care of the scale of the diagram. Now, because this will always be on graph paper in paper 2, so what 1 centimeter is, that might be different things on the scale of the drawing, right? So for example, the examiner tells me this, that the focal length is, let's say, 4 centimeters. And he tells me that one big box, so one box which contains 5 of the other boxes, that's 4 centimeter, right? So I just count those boxes and mark those points. So for example, maybe this is how F is, and maybe this is how the F is on the other side. This is the first thing to do. Now you've marked F on either side of the lens, you'll also have to mark 2F. So maybe if this was 4 centimeters, so 4 boxes to the right, if that's what the scale said, you'll go 4 centimeters further ahead and mark your 2F points. So this is 2F here, and then again 2F here. All right, so this is done. So the first step of the drawing is complete. Now you go on to the next steps. So the next step is this, that if this has not been done already, you would have to mark the position of the object. Now let's say this is how the question is. So you were given the focal length, you mark that, done. Now the examiner says that the object is positioned 10 centimeters from the lens. So if this is 4, then this is 8, then 10 would be somewhere here. Again, sometimes the examiner would also give the height of the object. You would also have to plot that according to the scale which is given. All right, so let me make this. So this is your object. Now what you do is you use any two of the ray rules to complete the drawing. All right, so now how do we do that? So again, the first one is the easiest one, rule number 1, ray number 1. So a ray through O is completely undeviated. I'll be using ray number 2. So a ray which is parallel to the principal axis gets refracted through F in this way. Where the rays intersect is the position of the image. So this right here is the image. All right, this is the image I. This is how you would complete the drawing. Then most of the times the examiner will also go forward and ask something else from you, such as this term, the linear magnification. So how do we define the linear magnification? It's basically just a measure of how big your image is as compared to your object. So it's a ratio of image height to object height. Instead of height, you can also say size, and that's perfectly fine. So for example, in this case, this length divided by this length, right? So image size divided by object size. Now that we've done the drawing, let me draw something else on here just to make this a bit easier to see. Let me take up a nice color, maybe something like this. Obviously, all of you who are appearing for IGCSE or O-level physics are also appearing for math. So have you ever seen a diagram like this in a math chapter? The answer to this is, by the way, yes, you would have seen this in the chapter called Similarity and Congruence. Now these two triangles are similar. I won't be getting into this debate of why they are similar. That's part of the math syllabus. So there's angle properties, side properties. I'm more interested in what it means in terms of lengths for triangles to be similar. So the idea is this, that if two triangles are similar, in this case this one and this one, then the ratio of the corresponding lengths is equal. Now, for example, in this case, what I just said is that this length of this triangle, the vertical, divided by the vertical of the other one, they are equal to the linear magnification, right? So this length divided by this length is magnification. You can also say it this way, that this length, which is the horizontal distance of this triangle, divided by the horizontal distance of this triangle, this can also be used to calculate magnification. So if I further define a few terms here, so this being object distance, this being image distance. So I can further also state the magnification in terms of image distance, and this distance is from the lens divided by the object distance. In case you're wondering, I could also do the same thing with the hypotenuse, but that's very tiresome because these lengths I can look at directly from the graph paper. For this, I'll need to use Pythagoras, which is a task in itself. So that's some basic information about lengths. Next time we'll be starting with the cases. So see you in the next video.